Physicist working at the TU München, and I'm part of this great Munich Quantum Science and Technology initiative. A warm welcome to everybody on this evening, the first evening of our annual conference. So I have the pleasure today, here the drinks are coming. I have the pleasure today to host the MCQST Stammtisch together with a colleague from the University of Hannover, Robert Raussendorf, who is heading there a group on quantum information. And I'm also joined by 4 other colleagues. So first and foremost, let me introduce Sophia Economou. She's from Virginia Tech, and she directs the Center for Quantum Information Science and Technology there. Then maybe another guest from outside the cluster is Thomas Monz. He's in a double role here. He's a researcher at the Institute of Experimental Physics in Innsbruck, but he's also the CEO and founder of Alpine Quantum Technologies. So a warm welcome to him also. And then there are 2 of my colleagues from TUM, Stefan Filipp, who's an experimental colleague at TUM, but he's also one of the directors of the Walter Meissner Institute of the Bavarian Academy of Science. And last but not least, my colleague Robert König, another mathematical physicist from TUM's math department, like myself, and he's leading a group on quantum computation there. So, as a topic of today's Stammtisch, we thought of not picking a topic which would go into the details and nitty-gritties of science, but something else for this time. Namely, we want to ask what makes quantum research tick. Okay, so as you all know, research is done by individuals, but it's also done in groups. MCQST is a great example how research is done in groups. And these groups are connected. Sometimes they work together, but each individual also has an own research agenda. And what we want to discuss today is, for example, how do researchers pick topics? And this is something which I want to start with. In fact, so let me ask you, what motivates you to pick a topic in your particular field? Maybe anybody of our guests could start. Stefan, do you? Or?
You mean not external guests?
No, maybe we can start with the internal guests. So what motivates you to pick a topic?
I mean, the general motivation is kind of what do you want to do in basic and what will you want to reach then in the long term. So that means for my case, I thought quantum computing is something that I would like to do. And then it's kind of what is the way towards this. And I think that's maybe also a difference to kind of having maybe more short-time goals or so, but then it's more like what is at the moment basically a trend that you're following, a trend basically where does the field go to and what seems interesting in terms of all of the kind of common knowledge that is at the moment there. What brings you further? So as an example, for example, you can notice there was at some point there was a huge interest in how to make 2-qubit gates. It does sound like a technological thing, but kind of what is the principles to go there? And then at some point, okay, you know how to do this, and then it shifts because then you figure out what is the limits to that, and then what is this tiny little things that actually makes my gates bad? Then you study, for example, what is the 2-level systems that are basically in the materials, and that's kind of then you pick kind of a route that goes to this overall goal, but then you might get some detours, and I think the thing is, or the main point is, just stick to your main goal. And because you can easily get a detour which leads nowhere. And so that's kind of research, how I pick topics is kind of more by the general interest, and then letting some detours be allowed.
So maybe this is also, I mean, you're an experimental researcher. This, I guess, also from my point of view, this looks maybe a bit different. And so maybe, Robert, you may want to add how the world looks like from the point of view of theory.
So I think what you're saying kind of aligns with how I think of experimentalists. And I think of
So
experimentalists
I'm curious
the wrong
to
way.
hear.
Cheers.
I mean this in a good way. I find this very difficult actually to have this kind of long-term vision, and I think personally at least I pick topics in a much more random way, I would say. So for example, it could just be an area that I know pretty much nothing about and want to learn about. So that's one reason to choose to go into a certain direction. And then as you learn what the topic is about and so on, you find sort of new directions and sort of. But I guess it involves a lot of dead ends also. So and maybe that's something we can afford to do as theorists, because we can sort of waste some time on a certain topic and then maybe realize that this is not that fruitful and so on. And I think experimentalists, you have a lot more constraints, so I'm very impressed that you can navigate this. And, I don't know what the other theorists...
I am kind of somewhere in between, I would say. So one thing, because there's a very young audience here, relatively speaking, and this is something my students do, so I'm going to speak from that perspective, is there's a gap in the literature and you need to fill it. No, you don't have to, right? Just because someone hasn't done X doesn't mean someone has to do it. There's full of gaps. So I think within what has not been done is identifying things that are of interest to you. Otherwise, you'd be bored if you're not interested in it, but also to the community. And that, of course, assumes you know the community that your research addresses, right? Because when you write a paper so that other people read it. You presumably don't write it for yourself only. So, and then in terms of big goal versus kind of what's interesting, I would say somewhere in between. So I like to inform my research with experimental constraints, because that kind of brings in something that makes it to me more interesting, because I don't just wander around theory land. But then I also want to have theoretical ideas to ground it in and connect it to. And also I agree with you in terms of this is interesting, I don't understand it, and you're in this kind of I'm still student mode and learning.
Thomas?
Okay.
Oh, sorry, I didn't mean to interrupt.
Okay.
Yeah.
So I think you could take a step back and think about like what do you perceive, or what do you want your profile to be? So in my case, I usually say it's like there are three things I like to work on. It's like experimental quantum info, yes, but it's roughly I want to understand the underlying physics. That means spectroscopy, characterization, techniques. The other part is I know there will be limits, as Stefan said. It's like, can I fix these by a deep physical understanding and find new ways of implementing as desired interaction? But then at some point, it's like there will be limits with the techniques that I have. So I can say, can I brute force it? So that's my second profile, is error correction. How could I do error correction on a quantum computer? What does it take? What are good ways of doing it, with resource-efficient ways of doing it? And the third one is, at the end of the day, I want to do and demonstrate some applications. I mean, it's going to be proof of concept, but at least it's like, let me show that we are moving in the right direction. And as you said, we don't go into a dead end for doing something for the sake of just doing it, but it's not bringing me and the entire field forward. And then within these three domains of roughly characterization, spectroscopy, error correction, and applications, it's like I'm fairly confident in my understanding on the experimental physics side. But what I like to do is I like to work with others, in particular, like partially outside the field. So that means I could go to a computer scientist and say, what do you need to use this device more efficiently? Is there a certain capability that the community is lacking, where you as a computer scientist looking at it from the outside would say, oh, if we could do some, let's say an if or a for loop, that would make my life so much easier. And then I can say, is there some trick that allows me on my platform to implement it? And then doing something where I say, now I can do something with a computer scientist, I can do something with a chemist, I can do something with an applied math person, where you can say, oh, few people do that. This interdisciplinary research is also not so much supported sometimes from the funding agencies. But if we go down that path, you can rest assured that you do something that A, is moving the field forward, because you get this feedback of this is something missing, and at the same time you do something cool that no one probably has done before. And that's how we try to motivate the field internally.
I believe that interdisciplinary science is a topic that we will come back to, and maybe Simone will come back, I don't know. But we share. So,
yes.
But Robert, I want to follow up on what you said. So you said, somehow that's stuck out for me. So you said, oh, yeah, there are topics I want to learn about, topics I know nothing about, so I jump right in. But you know, and I think the people on the table know, that even Robert König can know everything. And so you pick the subject that you learn about. How do you do that? Is it with like what Stefan said, is it with a big goal in mind, so you are maybe meandering around in a different way, that you think you need certain areas to reach your goal, or is it more educational interest? So what makes you pick these new fields?
I think it's both to a certain extent. I mean, one important aspect is, of course, my interest in a topic, and of course, I'm more interested in topics that perhaps align with some of my main research directions, obviously, because I don't have time to learn about every possible area, and so of course there are sort of areas of emphasis where I try to find things that I don't know within that area that could be useful to develop error correction or whatever I'm sort of generally interested in. But I think, picking a new direction really involves something new. So it's not that I just look at what I'm already working on and then try to continue on that. So sometimes I think you really have to try to acquire additional skills, and especially when you do theory, there's some papers coming out that are interesting to read and learn about. So.
Thank you.
I'm not sure whether this answers your question.
Good, you know.
I would be curious, but how long does it take you then actually to learn a new technique or so? Because it seems to be a matter of time scales. Yes. If I learn a new technique or so, it takes me probably months, years or something like that, so that it really works at the end. So if it was me that says it should work, then it's months or so. If then somebody does it, it takes typically years or so. I don't know what.
If I'm honest, it's probably the same.
Yes.
So it means you have time enough basically to first study.
No, I don't feel like I have enough time to learn new things. So I think the young generation has this luxury, but I wish I had more time.
So you also need a PhD life basically for learning a new tool or a new technique.
Yes, I mean, I think during your PhD and maybe also after that, you sort of have this freedom to say, okay, I want to learn. In my case, I wanted to learn about topological quantum computing, and I had no clue about it. And it was okay to do that for a while, until I sort of learned the basics.
So this is a bit the question, at which career stage does your research look how? But maybe let me come back, because I was tickled by your answer, which centers a bit around the question, the central question, what is good science? And how do we, as researchers, make sure that we are successful? and what constitutes success in our field? What would be your answer to this very broad question?
Yeah, so I think good science is like the Supreme Court justice who said you know it when you see it about pornography. I think it's kind of similar about good science. You kind of know it when you see a good paper. Okay, so that's like, you know, the easy answer. I think nice papers are kind of connect to me the way like people describe what do people find beautiful aesthetically and in art. It's some combination of the expected and the unexpected. So I think at that point, I think you get to the subjective, right? If you're reading a paper that has components of something you understand, but then it takes it to a different direction or adds elements that you didn't expect, that's how kind of I can describe the papers I find beautiful. And then, I don't know, well-written papers I think is important, no matter the result, to write kind of in an honest, accessible way.
I think this might look a bit different if you're more on the applied side, I imagine.
Not sure. I think good science is still you will recognize somebody has a brilliant idea and then a new way how to tackle or how to do a new type of resolving, a new way of looking at things. Or basically you can also say improving the precision or so by an order of magnitude or 2 orders of magnitude so that you can see the different aspects and then learn more about this. I think that's kind of, if you manage this, by combining, then we're back to interdisciplinarity probably, combining from different topics and then create something new. I think that's probably similar to that.
Like if I go by something that Peter Zoller sometime, or like at some point said or complained about was, if you find a new solution, which in hindsight is like, oh, that was obvious, that's like smooth, that makes everything easier. But it's only smooth and easy once you have solved it and understood it. And then it's like, why didn't we think about it 10 years ago? Because now the new solution, the new method, the new gate, the new material, it makes everything so, regardless of whether it's theory or experiment, if you say this is such a nice solution, but it still took years maybe to make this connection, to get this idea, this like someone prodding you at the conference with the right idea, and then it's like, oh, that's the right thing. Now we opened a cool new door that we haven't thought about.
Keep an eye on Simone. She is collecting her weapons, it seems. But I don't know. Maybe that's not up next. I don't know.
Yes, I mean, I think because I also asked about success, and you know, as you all know, in many hiring committees, because there are too many people in those hiring committees, success is sometimes measured in citations per year. But this might not be what success in good science looks like, and maybe, you know, something in which I think you should show because it's your graphics.
Okay, okay, are we at that point? Okay, good.
Yes.
So this is from a recent lecture. I teach a course right now on models of quantum computation, and so I was talking about quantum computation with magic states, and so I was talking about contextuality. And so I was starting with EPR. And so what you see here is the EPR paper of 1935 and its citations. And, yeah? Oh, sorry.
Yes.
Okay, sorry, it's not so we didn't magnify it. You can, it's from the Physical Review website. So who has their laptops here, you can look it up. Yeah, so these are the citations of the EPR paper. And so what I plotted here, or what Physical Review allowed me to plot is the citation numbers per year. So this is 35, and then there's nothing for about 3 decades. And then we are in the 60s and 70s, then Bell comes up, Kochen-Specker comes up. Then comes the experiment, then something happens. It's kind of a tiny lift off, so to speak, but still pretty close to the ground. And then comes Alain Aspect with the experimental verification of Bell inequalities and just continues at low altitude. And then something happens, which we haven't identified, and then is real takeoff. And then those numbers go up and up and up. Yeah, and so the paper today, one would probably say it was wrong, yeah? But it got so popular. So panelists, please explain to us what happened.
No, I love this example. I mean, just as countering your answer, I mean, because everybody would agree. I mean, you know when great science is done, you recognize it, but it's not recognized sometimes in citations until decades after.
Isn't this a sad story for theorists? You have to wait until the experiment is done and then it can be recognized.
But
No,
let me
it doesn't change much.
Let me point out the experiment was done here, right? And then there's still nothing almost.
Oh, but then it goes up.
Well, but it takes a while.
It's a decade, these
It takes kind of another
9
decade,
decades here on this plot.
and then it takes off. So things are complicated, but you wanted to add something.
I'm not sure I can explain this, but actually I wanted to add something about the notion of good science and actually mention an example that you contributed to. And I'm not talking about wrong papers here, but...
sorry, maybe I shouldn't have said that. Anka will cut it out. So.
Yeah, like models of computation, if you think about something like the one-way computer which you invented, I mean, that's just amazing to me because it connects to so many different fields, condensed matter physics, computation, also experimental efforts. I mean, it's so important that it's obviously, once you see it, you see that, okay, this is timeless, this is sort of textbook material, and it will sort of go down history. And then, of course, eventually it's picked up by experimentalists and so on, and it's realized. So I think this sort of connectivity and opening up new directions is an important aspect of things that I find very impressive in sense. But, yeah, I don't know about this graph. It also, I'm curious, like, it actually goes down?
No, this is just because it's May, that's why.
Okay.
No, this is this half year,
That seems very
2025.
strange. Okay. So it keeps going up.
Presumably, yeah.
Yes.
But isn't it, so what I said before, and making fun of it, but in principle, isn't it the story that you are telling is that somebody picks it up, isn't it? So that's kind of good science, and whether it takes them decades or only years or so, but it's the essence is that you have something that is picked up by the whole community, and then either creates different branches in different fields, or is then even, okay, you can now discuss whether quantum information science is useful or not, that's a different story, but at least it creates some application at the end. And then it's, I think, that's still a sign of a very successful paper and successful science that's done here.
But even kind of the contributions of Bell and Koch and Specker, which we of course recognize nowadays as just historic. I mean, they didn't change anything for a while until the experiment came.
Exactly.
Yeah.
Okay, so also the opinion of the audience is requested. If you want to make a conjecture about what caused this liftoff, yeah, please call us. Yeah.
But isn't this around the time sort of quantum computing started?
Yeah, it could be Shor's algorithm, for example.
Yes,
Yeah,
it's actually the middle of the 90s.
yeah. So maybe they.
That was my conjecture.
Yeah, it could be.
I guess it's related to asking what quantum is useful for, apart from designing semiconductors and so on.
Good. I mean, if somebody, I mean, we can say for sure. So, but we are inviting opinions, but I think that's a good candidate. Yeah. So here, if you see it that way, Robert, I apologize. Maybe I can ask you another question. So, if you see if it is true with quantum algorithms and so on and so forth, then it was the application that did the trick. Mm-hmm. So, Robert, I want to ask you about that paper with Sergei Bravy on topological codes in the Clifford hierarchy. So maybe I first need to explain to the audience a little bit of what this is about, because it's maybe not everybody knows this. So this is a paper in the theory of quantum error correction, and it makes the connection that was previously completely not thought of, inconceivable, about two important things in that theory. Namely, it talks about topological quantum code, topological stabilizer quantum codes on one side. So Clifford, the toric code came up earlier today, so that's an example about such kinds of codes, but not necessarily only in dimension 2. And on the other side, so it connected that thing to the so-called Clifford hierarchy. So the Clifford hierarchy is a hierarchy of gates starting with the very simple, that's the Pauli flips, then the next level, going to the harder gates. And so the next level is the Clifford gates, and then the third level you have a bunch of gates you need for universality, and it's getting harder and harder and harder. And this whole thing is organized by how complicated it is to do these gates in a state injection scheme. So, so what Robert and Sergei Bravy did, they connected these two notions, and they showed that topological codes, they become more powerful in the way that they can implement these gates further down in the Clifford hierarchy, the higher the dimension is that they live in. So it was, yeah, this was a fundamental result in the theory of quantum error correction. At the same time as it is about decoherence, and so it is about stabilizing quantum computation, and so it's about application. So, long story, Robert, what's your take on how the fundamental, the abstract, and the applied come together? And this question is really for everybody also, just I'm starting out that way.
Okay, so I guess if you're talking about this particular paper, I mean, it was really motivated by the application. We were wondering what gates can you do in a d-dimensional stabilizer codes, and what we found was that it had to do with a certain level of the Clifford hierarchy, so the abstract sort of was part of the answer. And so to me, I mean, abstraction by itself is perhaps not that interesting unless you're trying to answer some specific questions. I mean, if you think about the Clifford hierarchy, the whole concept was introduced by I guess, Gottesman and Chuang, and they also, they didn't just introduce it, but they were basically asking what gates can you do with gate teleportation in a certain number of rounds, and that was sort of the answer. So I think this is really nice when sort of the application motivates some theoretical considerations, and perhaps, I mean, I guess there are cases where things go the other way also, but to me the application or the operational question is more important.
Operational question is more important. Good, thank you. Other opinion?
I agree. I don't think I have much to add.
So I think, okay. So how does this? The question was kind of how does fundamental and application go together?
Yeah, the abstract concepts and the applications. How do they align in good ways?
I think there is both ways are actually conceivable and happen actually, because you could now basically in the light of MCQST argue you need broad research, you need kind of a basic research to actually then come to new ideas and new technologies, new methods, new insights or so that then will build up an application. And that's, I think, totally true, and it needs to be there, so there's this pyramid. But then maybe along this line, I've never seen this paper in this way, but it's the same way of thinking that technology then inspires also fundamental research. And then recently, when I came across this STM Nobel Prize, and then you think about how is the STM invented, and it was invented because you looked at Josephson junctions and you wanted to analyze now the materials and you wanted to understand what happens at this Josephson junction, why is it basically so bad or so. And then this was invented with a certain application in mind, and now it's born a huge research in kind of is it one basic tool in doing material science at all. So it goes back and forth. So I think there is no directionality in this exchange, and that's actually essential.
I think this is kind of an interesting point because we were talking about collaborations and being inspired. In your case, you didn't need a collaboration, but you had an application kind of as a motivation. So do you, when you say somehow you are inspired by theorists, are you working together with theorists in any of what you're doing?
So sure, I think we're always in exchange, and maybe that's also okay. But personally, for sure, and that
so
you have to.
How close are these collaborations? Do you have a project, and then in some of these projects, a theorist is present?
Ideally.
Okay,
there's a whole story around that, and I think personally we are at the moment more in this technology stage where we want to do things and need to basically go really into this doing new methods. But at the end, what we also need to actually do is to connect this to theorists, concepts, maybe simulation, but maybe also some analytical understanding of what goes on. And I think this is a back and forth. Personally, at the moment, we can improve on that. Also because, I don't know whether I should make this point again, because theorists tend to not go into the technology because they're kind of shying away in wanting to understand what's really going on when you want to do technology. But it's more you want to abstract away and say, I'm a pure theorist. But it's actually would be much easier to meet in between somewhere so that experimentalists go a little bit up in theory. And I think that's the best way to do experimentalists, but also theorists go down to the experimental.
Maybe Thomas, because you already reported about these collaborations, maybe you want to add.
So my favorite theorists tend to be the ones, Robert would maybe not so much sit in the lab, but if you think about a good colleague of ours, Markus Müller, has a couple of PhD students, and in particular, for instance, Friederike Butt. She comes into the lab. She comes in. She goes to the secretary. Patrizia gets her key, and she sits in the lab with the first coffee together with the rest of the team. And not so much that she uses the device, but she's sitting there. She gets a feeling for the device, and she can look, and she's like, "Can you do the other thing?" And then Vanya or Christian or Marcel, they sit there, she's like, sure, we can do that. It's like, why haven't you told me? That makes, now I have a neat trick that makes everything so much easier. It's like, well, for us it was obvious. We didn't know that you wouldn't know that we can do that. And the very moment they sit there together, suffer in the lab together, it's like almost, and we do it the other way around. I remember, for instance, with Miguel Angel Martin Delgado in Spain, topological codes, and he whipped us through where does this threshold come through, and it was like speed dating with thermodynamics and where the threshold comes from, and it was like, wow. But at least now I had a rough idea of where it came from. And then we're like, but we can play this trick and play this game, and does it make it easier? And suddenly we had new ideas on how to implement certain applications in the device, or what you nowadays might call co-design, where you say, how does Stefan design his next chip? There were neat examples, for a long time, the superconducting people started with, there's the surface code, so we do everything in squares. And then it's like, oh no, maybe we should do a hex code. There might be some technological advantages for this. Like, where do we place the ancillas? And you have to think about what does the theory want, what can the hardware do, and then having something where you say you meet in the middle ground, but you can't find this middle ground if you never ever share a coffee together.
Is that kind of the same experience which you have kind of in your lab in Virginia?
Yes, personally I agree. And I've been, I was brought up to collaborate with experimentalists, so I kind of try to pass this to my students. Some have resistance, some of them want to do theory, only clean, don't contaminate it with anything dirty. But I think it's good for them, even if they don't go heavily in that direction, to get exposed. And a lot of physics is down there, right? It's not just engineering, whatever that means. Yeah.
So which kind of brings me to another question. what is the role of these different sub-disciplines which are gathered at this table? So we have kind of a representative from a more industrial perspective on the field, and on this side of the table we have mathematicians, which are probably representing a completely different ecosystem of the field of quantum science. So what in your opinion kind of is the role of all these disciplines? What's the role of kind of an industrial aspect?
You could put it that way to say it's ideally a natural extension of where like research could lead to. It doesn't have to, but it could lead to. Where you'd say you start with an idea, the idea gets fleshed out in more detail, someone picks it up and says, I want to turn this idea into reality, and he's struggling it, and then someone says, like, now we have this thing, and you stumble upon a neat application, and someone says, oh, this can find a use case, I don't know, in biology, in medicine, in something. And then you could sit back and say, maybe in a couple of years, it's like, okay, it did 3 different turns that I did not expect. But now this idea, 30 years later, might be in your cell phone or something. And that would be like an interesting path for ways like how does an idea grow and move on forward? Because at the end of the day, you could say it's like similar to our research where you say we initially judged. I mean, I would not agree that like the citations would be the real measure for was it good research, or it shouldn't be the sole measure.
I think we saw it.
Yeah, but you could say it's like, wouldn't you be then saying it's like if others build on top of my idea, to say they see value in that work because they build on top. Then you could so say I go from your brainchild towards proof of principle to applications.
Right, but then these industrial applications, I can be now very provocative because it's my colleague, Stefan. I mean, you know, you're working at a university, you're working kind of for a company which you founded. Do you think that universities at all should engage in competing with industry?
I don't think they don't compete. That was too much negation. I don't think they compete because they have different goals. Ideally, they help each other. So like there would be a cool idea, and maybe a company says this is the right direction. Let's support Robert some more because we need maybe not the idea now, but we see that it's moving in the right direction. We have the trust in him or in Sophia. And say, let's fund a PhD student for 2-3 years. This is something that companies can enable, and they do enable that. And the cool thing there could be that they enable that even if a funding agency might not enable that.
So maybe
but isn't it more like what you had at the interface between theory and experimentalist, so that you have to, as an experimentalist, you have to understand a little bit of theory at least, so that you can talk to each other, and as a theorist you should be able to understand the experimentalist. So isn't it in the same, like as an industry you have to understand how university works, and as a university you also have to understand how industry works? And because that's kind of, I'm saying this because we are just learning this actually, because I was raised as a researcher doing my master's, PhD or so, and then at some point this whole quantum thing
come on, you were at IBM, so.
Later, yeah. Before I did a PhD, yeah. I think this concept of industry PhDs, I don't know whether it was around at that time, at least not in our community. No. But that's, I think, is the exciting thing, is it now that we get this intermingling, and yes, and then you can ask, should we do company-style research in universities?
Yes.
Oh, that's
a different question.
So maybe you're the right one to
no,
give
I'm
a
asking
first
the
answer.
question, I'm not answering.
Well,
so I think
you could actually turn it on its head. You could say, could the university even afford that? Because when you think about the normal grant, at least in the Austrian case, it's like you're happy if you get the postdoc and a PhD out of it. And now you would say, take how much researchers is IBM throwing at quantum? Is that even the right comparison to say the university does industry scale research?
Yeah, but now it's really a large scale, is it? If you say like quantum computing costs billions, basically, then it's a no-brainer that you cannot do this at the university. Say you have a small company or so, you start a little bit, and then you get going with from your PhD and postdocs or so, and then you start a small company. I think that still has relevance within the university, and then you grow it up. And then you try to find the link. So I think there is also this technology transfer question is important to my understanding, at least for experimentalists. I don't know, back to the theories.
But it's not like
technology.
Like theories also have spin-offs.
Yeah, that's what I'm, yes, they do.
Not only experimentalists have spin-offs.
So how important is technology for you? For you both?
You mean sort of the transfer? Or?
Yes.
To me personally, perhaps not very much. But I think I see this more as sort of a division of labor thing. I mean, we can all coexist and do what we like to do, and hopefully do it well. And I think many of us theorists wouldn't be comfortable in a lab, suffering in the lab, or we would be too afraid of breaking things, for example.
Yeah, also
part of the game.
Suffering.
So and I think it's the same with commercialization and so on. I think some people do this very well, and they might also have different interests. And then these big experiments, you need a large company.
You could say the same, or you could ask the same question, but drop the word quantum. I mean, in chemistry, there is a clear connection. In medicine, there is a clear connection. Why do we make quantum special? Why would we perceive quantum to be different, let's put it that way, compared to seeing how there has been synergy in essentially every other field, whether that's math, chemistry, bio, medicine, and so on, for several decades. It's just that it's younger, I fully agree, but at least in other disciplines, it's been there since the early days.
Yeah, that may be a good point. And you know, I mean, sometimes actually, in particular, if you work in the mathematical science, you could not even prevent that something could become applicable in the very end. There's this famous story of Hardy, who was extremely proud that his research was not applied in comparison to Littlewood's research. But that was true during the time of the war, where Littlewood somehow wanted to support the war effort, as far as I understand, and Hardy didn't. But in hindsight, Hardy's results are probably more applied now than what Littlewood did. So in our field, I think, so kind of the very theoretical side, you don't even know whether things would, in the end, grow legs towards real applications.
So that means as a researcher, you don't even should actually have in mind that there is an application, you just do research. And then at the end, you wait for whether it's going to be successful or not.
I think it's just differently driven. It's not, you're not so much driven by, sort of in the end, I want my research to advance Stefan Filipp's chip. But
nice to advance our
but rather I wouldn't mind, right? Mathematicians probably look, as Robert has emphasized, and as you've also emphasized, we are sometimes driven by internal beauty, and that can grow application legs, but many of us don't care.
But you could also, say, on an individual level, you might not care, but the money is coming from somewhere. Like, what's the interest of the state in giving you money? It's like, is the state as a funding agency so altruistic to say is like we support all the research just because we have spare money?
Thanks, I didn't dare to ask the question.
Yeah, okay, the benefit is good. Or is it more like the state does have its own interest in saying there are specially trained people where the majority of them will not go into academia, and so we have very well-trained people that can support, let's say, give it a cutting edge in industry. Because it's like how many, let's say, how many PhD students have you trained? How many stay in academia? And then, in some sense, all the people that you trained supported giving certain companies a competitive edge by their knowledge and experience. And so maybe it's not so much about you, but what you enable, like the next generation that you enable by being very well trained in a certain field that the funding agency deemed to be important for the coming decades.
Yes, that might be true. But actually, sometimes things can really grow direct legs to more applications. So, I don't know, let me give you a spontaneous example because I was triggered by your lecture, Robert, where some of these error correction and fault tolerance models are based on research in
You're looking at me. You just totally derailed me. But
yeah.
we get to that later. We get to that.
Sorry.
Simone, please.
So by things which actually come from spin glass research, right? And that's a totally different universe. Typically, you are not connected to that, but part of my math background is connected to this, and so I can actually, in some sense, then serve as a bridge. That is, I think.
Looking forward to it.
Yeah. Yes, we should collaborate more. But I think that is in a very good sense the role of a mathematical physicist. That you know about maybe sort of a different set of techniques which you then bring to the table, which at first I don't know if this might be successful. Very often, as we all know, as theorists, we run against a wall, and then we have a stupid suggestion, and it just goes nowhere. But once in a while, this might even lead to, in the end, a better fault-tolerant algorithm. Why not? I derailed you. I derailed you. Cheers.
You too. Oh my God. Yeah. So, okay. So let's maybe summarize a little bit. I mean, Simone, the way I understood you laid out a certain mode of operation. So maybe you are guided by aesthetics, by consistency. You wanna make rigorous things and compact things and beautiful things, and then you just throw them out like these beautiful cookies and out in the world. And then maybe if you are lucky, somebody some decades later will pick them up and make something useful out of them. So that seems to be that mode of operation that maybe you are advocating. And then there is this more kind of directed research that Robert was mentioning earlier. So they just wanted to deal with that decoherence problem, and in the end kind of accidentally came up with a very fundamental relation. So there's different modes of operation. And yeah, when I heard Thomas talk, I thought it was time for a Zeilinger quote. I think we now have to get to that. And it goes again to that modes of operation. So we have here two quotes about operating in the field of science that are maybe not diametrically opposed, but certainly distinct. So one is from a national quantum strategy consultation in Canada. So it's a report that some branch of Canadian government conducted and wrote, and it's from 2021. So anyway, let me quote from that. Early engagement with end users will encourage collaboration between academia, industry, and government, help to target application development, and support commercial adoption and acceptance of quantum technologies. That's viewpoint number one. Viewpoint number two is from the New York Times, quoting Anton Zeilinger. And Zeilinger reportedly said, when we received his Nobel Prize, my advice would be, do what you find interesting and don't care too much about possible applications. So, does any of these points of view ring a bell with you? Any opinion on that matter?
For their respective field, both can be correct.
Mm-hmm.
If you are blue sky fundamental research and you might not even know where it's going, and if you get this carte blanche from the funding agency, where you essentially can say, I'm Robert, and that's why I get money, and that name is good enough, it can be very valuable and cool, like to get to this point where you essentially have to say, it's like, someone has that trust in me to say, you'll figure something out, something cool. In the early stage, you have to convince someone to say, is it moving in the right direction?
Thomas is now giving advice, it seems.
There is a template which the funding agency gives you, and it's like, we both know from certain templates, when you write an application, it says background, state of the art, which problem are you solving, what's the solution, how is the solution novel. You can't get around certain fields in templates. I agree with both of them. The question is whether you have the freedom to pursue one or the other.
Okay. Robert rose his hand. Did you?
I think I object to this a little bit. I think it sounds to me a little bit like the same kind of misconceptions I have about experimentalists, that we sort of sit around and have brilliant ideas and people trust us in having brilliant ideas. I don't really think it's that way. Like maybe if you're lucky, you get a great idea once every 10 years or something. But there's a lot of work that still needs to be done, even if not every idea is on the same level as this once-in-a-decade discovery. But in terms of these two statements, I guess personally, I think you have to be interested in what you're doing, and I think that there must be the same for you also. And that's sort of the first and most important thing to me. And I don't know.
Yeah, no, I agree. And I don't think anybody's entitled to being paid to do what only they find interesting, right? I mean, maybe there's a utopia where that happens, but it's not realistic. I think this quote from Anton is kind of the plane with the bullets. Once you're super successful, Nobel Prize winner, or almost there, then of course, you can do that. Probably not a great advice for junior people.
But ideally, there's some intersection between the things you are interested in.
Of course. I don't think any of us would have gone into science if, making money or following direction was the drivers, right?
But isn't it still a bit of an advice, kind of, that do trustworthy research or so? Don't oversell, or just do it well, basically, and then you get the trust. But I think this is getting a trustful relation with your funding agency, or being trusted in what you are doing. I think that's the essence of doing research. I mean, it's if you're hired as a PhD, I typically trust people that they can do what they are up for, or the funding agency trusts you that you will be the one who does the job. And if you can explain them why this doesn't work, but the other thing worked, then I think you're probably in the same situation that Anton Zeilinger is, because it's just, you can explain it. It's just, you shouldn't basically bullshit around in what you might have been done, but for some reason you couldn't done, because in the very beginning you said you're exaggerating tremendously. I think that's also the essence of being able to build this trust.
Currently we have this nice example in Austria. We have this Quantum Excellence Cluster, where really essentially the funding agency gave the quantum community a certain amount of money and say more or less self-organize on good topics. And that's a certain level of trust where you say if internally you have the right board, where you say we don't want to overburden you with bureaucracy and writing 10 different applications and so on, but it's like do your internal, let's say 2 or 4 pager and pitch it internally and you can get funding for 2-3 years. That's very close to this ideal world where you see very little bureaucracy, a good idea, and I can pursue it for 2-3 years.
I think you're a few steps ahead of Germany and Austria.
I don't know how you organize your clusters, but in our case...
Okay, the cluster is actually a good example where it works, yeah?
Yes. But that one is a really nice one. It's like little bureaucracy. I mean, the cluster was the bureaucracy. But now internally we can pursue relatively blue sky research with little, let's say, it's like internally if we say this is the right thing to do, then we can push forward.
Right.
Are we wrapping up, Simone?
Yeah, maybe kind of in the
Audience, huh?
Yeah, in the interest of me that we all want to go for dinner at one point, we should think about wrapping up. I hope what this discussion showed is that there is no kind of golden bullet path to doing good research, but there are a variety of paths. And there are also kind of different ways you could come up with picking your motivation and agenda, and I think all is probably valid and successful in the end. Scientists come in various varieties. Is probably Dyson, if I may end up with this Dyson quote, which I like a lot, who pointed out that great scientists come in 2 varieties. One are foxes and the other hedgehogs. The foxes meander around and pick today this research topic and then wander to the next research topic. You can be successful as such a person. Feynman is attributed to be a fox, but then other people are hedgehogs and they just dig deep holes in one spot. This is also a way to operate. Supposedly Einstein was a hedgehog. He didn't do a lot in a broad perspective, but we all agree that he was a great scientist and what he did was just trailblazing. So we all became scientists. Kind of one question which I want to end this discussion with is a personal question to each of you. If you wouldn't have become a quantum researcher, what would you have done with your life? Well, we could start, right?
Me, okay. Good, so let's start with me and end with you?
Yes.
Good. Okay, so if I had not become a quantum researcher, I probably had stayed a physicist.
Is that cheating?
All right. So, I wanted to become a high-energy physicist at one point. That didn't work out. I ended up in a math department doing quantum research.
I guess I always wanted to be some kind of scientist. Now I'm a quantum researcher.
So when you say quantum, you mean anything that has to do with quantum, condensed matter, quantum optics, all that is out? Or can I cheat like Robert?
I cheated.
I think if the question is if not a physicist, I would also be interested in all the other things. I used to like the idea of being a Supreme Court justice because you kind of solve puzzles in some way and look for consistencies and inconsistencies. It's a little bit like, you can view it from a scientific puzzle, but then, the last 5 years, I definitely would not want to be Supreme Court justice. And then I also like, I think architects I also like, and I think there's connection to science. There's a connection, something between beauty and exactness. So yeah, I'm answering like totally not the scientist path. But I like that I'm not all that and I'm a quantum scientist. Yeah.
Stefan,
Tough question.
what has the world lost?
I don't know whether it has lost something.
If you hadn't
I think
become a quantum scientist?
actually I couldn't decide whether to study physics or to study politics and philosophy. So I ended up doing physics. So maybe if I would have studied the other thing, I wouldn't have become a physicist, then I would now be an Uber driver or a taxi driver.
I think in my case, it's and that might help everyone in the room. It's like, think about what you like to do, think about what you don't like to do. Quite often the younger ones have it easier to say what they don't like to do, in order to choose which direction they should think about and go into the future. For me, if you now ask me, what would I do if I'm not a physicist? It essentially would be, it's like, what do I do when I'm not in the lab? Because shouldn't that fulfill me? It's like if I go outside of the lab, that I go home and I enjoy what I do. It's like, okay, obviously you would want to go back to the lab on the weekend, but no, for me it's like, I very much enjoy mountains and forests and everything outside. So I could be a mountain guide, I could be, which I wanted to be when I was young, like a veterinary for farmers. But I think something like mountain guide, ranger, hunter, something like that. That's typically my weekend anyway. And so you could say whenever I'm not in the lab, I do the other thing that really makes my heart beat. And so like if you are not in the lab, try to think whether the other part, that where you'd say this would be my second leg, if physics doesn't work out, then you could say, oh, but my weekend, my second half, or let's say not half, but the second half of the week, that should be the other part which my heart beats for.
All right, I think that's a very sort of good end of this discussion. And thank you all. Thanks to the panelists. Let's give them a round of applause. And see you at the next Stammtisch.
Cheers.
Cheers. Cheers.